Welcome back, IB mathematicians, to another exciting lesson with Learn Math by Example. Today, we're diving into the essential skills of bearing, a concept crucial in navigation, surveying, and even rescue missions. Imagine this scenario. A lone lighthouse keeper during a stormy night spots two distress signals. From the lighthouse, let's call it point L, ship A is observed at a bearing of 045 degrees and 5 kilometers away. At the same time, ship B is spotted at a bearing of 120 degrees from the lighthouse. The crucial piece of information for the Coast Guard is that the distance between ship A and ship B is exactly 7 kilometers. Your challenge is to calculate the distance of ship B from the lighthouse. This is a classic IB style problem combining geometry and trigonometry. Now we'll return to this mystery later on, but first, let's build up the foundation knowledge to solve it. So in this lesson, we will cover the fundamentals of bearing, learn how to calculate bearings in both simple and non-right angle triangles, and understand relative and back bearings. So let's begin. At its core, bearing is a way to describe direction, universally understood and incredibly precise. Now, there are three critical rules for bearing in the IB diploma program. First, all bearings are measured from north. So imagine a vertical line pointing straight up from your starting point. That's your north reference, representing 000 degrees. Second, bearings are always measured in a clockwise direction from the north line. And third, bearings are always expressed using three digits. So 45 degrees isn't just 45, it's 045 degrees. This three digit convention prevents confusion and ensures accuracy, especially in complex navigation. Now let's see some examples. A bearing of 045 degrees points exactly halfway between north and east. A bearing of 180 degrees points directly south. A bearing of 270 degrees points directly west. And a bearing of 315 degrees points halfway between north and west. Remember, we always start from the north, we measure clockwise, and we use three digits. Okay, got it? Now, a common concept in bearing problems is the idea of a back bearing. Finding the bearing from point B back to point A given the bearing from A to B. Imagine you're at point P and you measure the bearing to point Q as theta. Now, if you then travel to Q and want to find the bearing back to P, this is your back bearing. Crucially, the north line at P and Q are parallel. This means we can use properties of parallel lines and transversals. If the bearing from P to Q is less than 180 degrees, then the back bearing from Q to P is simply the original bearing plus 180 degrees. For example, if the bearing of Q from P is 075 degrees, then the bearing of P from Q is 255 degrees. Conversely, if the bearing from P to Q is greater than or equal to 180 degrees, the back bearing from Q to P is the original bearing minus 180 degrees. So if the bearing of Q from P is 290 degrees, then the back bearing of P from Q is 110 degrees. While we're discussing this, it's worth noting that in real-world navigation, you might hear relative bearing, which is an angle relative to your own heading. But in IB math, unless specified, bearing always refers to the true bearing measured from north, clockwise. Often calculating a bearing involves trigonometry, especially when dealing with right angle triangles. So let's say we want to find the bearing of point B from A. Imagine A is our starting point. We draw our north line upwards from A. Now point B is located 8 kilometers east and 6 kilometers north of A. This creates a right angle triangle. Now, to find the angle between our north line and the line connecting A to B, we first need to find angle theta or angle BAC. Now, since we have a right triangle, let's think about SOHCAHTOA. We have the opposite and the adjacent, so we can use the tangent ratio. Tangent theta is equals to opposite over adjacent. So in this case, that's 6 divided by 8. Calculating this using our GDC, theta is approximately 36.87 degrees. Since the angle is measured clockwise from north, our bearing alpha is the complement of this angle, which is 90 minus 36.67. So the bearing of B from A is approximately 0.53 degrees to 3 significant figures, as this is common in IB questions. Now, what if you wanted to find the bearing of A from B? Now, this is called the back bearing. In this case, we draw a north line from B. Because the two north lines are parallel, we can use our knowledge of parallel lines and transversals. So the angle we found is 53 degrees. It is alternate interior angle to the angle formed by the south line at B and the line BA. So to get the bearing of A from B, we add 180 degrees to our initial angle, giving us 233 degrees rounded to 3 significant figures. And remember, we rated 233 degrees. While right angle triangles are common, many real-world bearing problems involve non-right angle triangles. Now, this is where the sine rule and the cosine rule become indispensable. Consider this. You are at point A. From A, point B is at the bearing of 040 degrees and 10 kilometers away. Point C is at the bearing of 110 degrees from A and 8 kilometers away. Now we want to find the distance between B and C. First, we can find the angle A in triangle ABC. It's the difference between the two bearings, 110 degrees minus 40 degrees, which gives us 70 degrees. Now we have two sides and the included angle, the perfect setup for the cosine rule. Applying the cosine rule, BC squared is equal to AB squared plus AC squared minus 2AB times AC times the cosine of angle A. Now substituting our values, BC squared is equal to 10 squared plus 8 squared minus 2 times 10 times 8 times cosine of 70. This gives us BC squared approximately 109.276777. So BC is about 10.5 kilometers rounded to 3 significant figures. Now let's go a step further and find the bearing of C from B. For this, we first need to find angle ABC. We can use the sine rule in this case. 8 divided by sine of angle ABC is equal to 10.453553 divided by sine of 70 degrees. Solving for sine of angle ABC, we find that ABC is about 46 degrees. Now, to get the bearing of C from B, we draw a north line at B. Remember, the bearing of A from B is the back bearing of A from B, which is 180 degrees plus 40 degrees, which gives us 220 degrees. From this line BA, the angle ABC is 46 degrees. The bearing of C from B is therefore 220 minus 46, resulting into 174 degrees. This is how we tackle non-right angle triangles in bearing problems. Okay, now it's time to crack the Lighthouse Mystery. We need to find the distance of ship B from the lighthouse, which we'll call LB. First, let's visualize the situation. We have the lighthouse L, ship A and ship B forming a triangle LAB. We know the bearing of ship A is 045 degrees and its distance LA is 5 kilometers. We know the bearing of ship B is 120 degrees and the distance between ship A and ship B, AB, is 7 kilometers. Step 1. Now, let's find the angle inside our triangle at the lighthouse, angle ALB. This is simply the difference between the two bearings, 120 degrees minus 45 degrees, which gives us 75 degrees. Now we have a triangle where we know two sides, LA and AB, and the angle opposite one of the unknown sides, angle ALB. More importantly, we know two sides, LA and the unknown LB, let's call it X, and the included angle ALB. Now, this is perfect scenario for the cosine rule. The cosine rule states that AB squared is equal to LA squared plus LB squared minus 2 times LA times LB times cosine of angle ALB. So let's plug in our values into this formula. So 7 squared is equal to 5 squared plus x squared minus 2 times x times 5 times cosine 75 degrees. This simplifies to 49 equal 25 plus x squared minus 10 times x times cosine of 75 degrees, which is approximately 0.258819. Rearranging this into a standard quadratic equation, we get x squared minus 2.58819x minus 24 is equal to 0. To solve this equation, we have to use the quadratic equation. X is equal to negative b plus minus square root of b squared minus 4ac all divided by 2a. Substituting our values now, we get x is equal to 2.58819 plus or minus the square root of negative 2.58819 all squared minus 4 times 1 times negative 24 all divided by 2 times 1. Calculating this using our GDC, we get two possible solutions for x. One is negative, which we can discard as distance cannot be negative, and this is very important. The other solution is approximately 6.36 kilometers. So the distance of ship B from the lighthouse rounded to three significant figures is 6.36 kilometers. Mystery solved. The Coast Guard now has the vital information they need. And that's bring us to the end of our deep dive into bearing. We started with a thrilling lighthouse mystery, then systematically built our understanding from the fundamentals of north, reference, and clockwise measurement. We then mastered calculating bearings in both right angle triangles and complex triangles using trigonometry and explored the relationship between forward and back bearing. Remember, always measure from north, always clockwise, and always use 3 digits. Do not be afraid to draw diagrams and use your sine and cosine rules for non-right angled triangles. If you have any questions or want to discuss more problems, share your thoughts in the comments below. Engaging with the material and your peers is a fantastic way to deepen your understanding and analytical skills in mathematics. To check your understanding right now, head over to our website to do some practice on bearing. Until next time, keep exploring the wonders of math.